Hello there students and welcome to another session of our revision series of class 11 physics. So we will continue with the system of particles and the discussion about collisions today. So this is system of particles. Session number 6 for revision. So we are discussing about collisions of a particle with a rigid surface last time. So let's start with a review question example problem of that. So let us say we have a situation like this, that we have an inclined surface of angle of inclination 30 degrees, and a particle is dropped from a certain height above the inclined plane. So a particle P of, let's say, mass 200 grams dropped from a height, let's say h is equal to 20 meters onto the inclined surface, collides and develops a horizontal velocity v just after the impact. So what we want to do here is we want to calculate the value of this horizontal velocity v. We take g as 10 meters per second square. Secondly, we want to calculate the coefficient of restitution for the collision. And we also want to calculate the collision impulse acting on the particle due to this particular impact. I'll just leave you with a minute to go through the question, then we'll discuss the solution in detail. All right, so let's go through this then. So what's happening here is that first of all, the particle falls freely under gravity through a height of h starting from rest. So it will have an impact velocity so by the time it collides over here, it will have an impact velocity, let us say u, which is vertically downwards. So u will be equal to root 2 gh. Okay. It shall in this case become 20 meters per second. Okay. Now what will happen is, as a result of the impact, where the collision impulse acting on the particle will be along the normal axis. So on the particle, the collision impulse that will act along, let's say, this direction, which is normal. So this is the collision impulse which we will calculate in the last part of the question. But more importantly, this will act along the normal. Whereas along the tangential direction, you can see there is no impulse acting. Okay. And now given to us in the question as part of the data given, or as part of the condition given, or the observation given for the question, is that after the impact, immediately after the impact, the direction of motion of the particle is horizontal. So the final velocity after the collision impulse acts on it will be in this sort of direction. This is V. Okay. So we can see that the collision impulse acting is equal to the change in momentum. So it is mv minus u. Okay. But we will obviously apply the component algebra over here. So again, in this diagram, I'm drawing the tangential axis and the normal axis. So I can see this angle is theta, and similarly in this diagram, drawing the normal and the tangential axis, I can see this angle is theta. Now applying the collision theory concepts that we discussed in the last session, we will see that first of all, tangential component of momentum is conserved. So we can see that the tangential component of momentum before impact was mu sine theta, whereas just after impact it is mv cos theta. So this tells us that v is equal to u tan theta. So this is our first equation, and from this we can see that v is equal to 20 meters per second multiplied by tan 30. So it is 20 by root 3 meters per second. So that becomes the first important result. Okay. Now the second thing is that separation velocity should be equal to coefficient of restitution times approach velocity. Okay. So separation velocity is the normal component of v. So that is v sine theta, and approach velocity is similarly the normal component of u. It is nothing but u cos theta in the diagram. So you can see that v sine theta should be equal to e times u cos theta. Okay. So substituting this result, we can see 20 by root 3 into sine 30 is equal to, because remember theta is equal to 30 degrees. Okay. So that is equal to e times 20 into cos 30, which is root 3 by 2. So from this we can see the coefficient of restitution comes out to be 1 by 3. So that is the other important answer. So this is the answer to part 1. This is the answer to the second part. Okay. Likewise, now the answer to the third part, the collision impulse, it is basically equal to this So in terms of magnitude, you will see it will become a normal component, which is minus minus, so it will become plus because the direction is reversing the normal component, which is u cos theta. So when we just apply component algebra to this equation, we get this one here. So the collision impulse will be 0.2 kgs multiplied by 20 by root 3 into half plus 20 into root 3 by 2. So 8 by root 3 kg meter per second. This will become the magnitude of the collision impulse. So this is the answer to the third and final part of the question. So I'll just leave you with a minute or two to go through this solution, and then we'll come to the next part of collisions. Okay, so that is about this particular question. Now, next up, let's look at the next aspect of collisions, which is the oblique collisions between two bodies or two particles, such that linear momentum alone is transferred, not angular momentum. But the linear momentum transfer does not coincide in axis with the collision axis or with the line of impact during the collision, which is why the final momenta are not along the same axis as the initial momenta, and hence it is an oblique or two-dimensional collision. So let's understand that kind of situation. So two-dimensional uh, oblique collisions between two bodies or two particles. So in a situation like this, generally speaking, if something like this is happening, like a body of mass m1 moving at an initial velocity u1, and another body of mass, body or particle or sphere or whatever, moving at initial velocity u2, mass m2. Suppose they make an impact such that at the time of impact, their situation is something like this, let's say. So as you can see, the collision impulse will be acting along this center to center line when they come in contact. So that will not coincide with the direction of the initial momenta vectors. Hence, the collision is two-dimensional. So when they come in contact with each other, the impulse which they will be applying will be in this sort of direction. These two are equal and opposite. Okay, and as a result of that, what might happen is that after impact, this might go off in this sort of direction, and this might go off in, let's say, this sort of direction. So the final momenta, these particles after the impact, might be along some axis like this, and axis like this, let's say. So they go off in these sort of directions. Okay, so after a while, we see that these particles or these bodies have final velocity vectors which are like this. So the idea here is that momentum conservation for the system consisting of the two colliding bodies, conservation of linear momentum, and give us this relation that where u1, u2, v1 and v2 are coplanar vectors. which are also coplanar with the impulse, the collision impulse. The collision impulse that is acting. So this equation in turn will generate two component equations. So from this we'll resolve this into two component. So on resolution, we get two component equations. And then of course we'll use the condition that separation velocity is equal to E times approach velocity. So that will give me one more equation. Okay. And using all this, we solve the given situation. So let's look at an example to understand how this works out. So for example, let's say we have a situation where this particle of mass m1 moving at a velocity u1 along this sort of direction makes an impact with another body moving in the equal and opposite direction. I mean, exactly opposite direction. So given that u1 and u2 are anti-parallel vectors with magnitude of u1 equal to magnitude of u2 equal to, let us say, 12 centimeters per second, and m1 is 20 grams whereas m2 is 50 grams. Okay. Now immediately after impact, m1 deflects by 90 degrees and m2 deflects by 53 degrees. So from this information we have to find their velocities v1 and v2 after impact, and we have to find the coefficient of restitution. Okay, so let's understand this question. Just give you with a minute to go through it, and then we'll discuss how we'll apply the conservation of momentum in two dimensions, and along with that the concept of coefficient of restitution as the ratio of separation velocity to approach velocity. So these are the two things we'll use to solve this question. Okay, so let's look at the solution of this question in detail. So what we'll do here is we'll take this is our XY system. So just before coming in contact are two spheres. They are moving in opposite directions. So one is moving along the positive x direction and the other is moving along the negative x direction. So the system's momentum momentum of the system is the vector sum of m1 u1 plus m2 u2. So that basically becomes, let's substitute the values. So you can see that this will become 20 grams into 12 minus 50 grams into 12 I cap. So that is minus 360 I cap in grams centimeters per second. This is the momentum of the system. Okay. So that's the first thing. Now, just after impact, what is going to happen is that this body which was going along the positive x direction, this now gets deflected by 90 degrees. So its velocity becomes along the y-axis. Whereas this particle that was going along the negative x direction, this gets deflected by 53 degrees. So its velocity will be in this direction, with this angle equal to 53 degrees. So the momentum of the system just after impact is equal to m1 v1 plus m2 v2. So this momentum becomes 20 into some v1 j cap, and this becomes 50 into minus v2 cos 53 I cap minus v2 sin 53 j cap. Okay. So the total momentum of the system, you can see, will become minus of, now cos 53 is 3 by 5, so minus 30 v2 I cap plus 20 v1 minus 40 v2 j cap, so in grams centimeters per second. So this becomes the momentum of the system after, just after impact. So conservation of linear momentum tells us that this initial linear momentum should be equal to this final linear momentum for the system. So this tells us that minus 360 I cap in grams centimeters per second should be equal to minus 30 v2 I cap plus 20 v1 minus 40 v2 j cap. So this tells us that 360 is equal to 30 v2 and 20 v1 minus 40 v2 is equal. So that's the second equation. So from the first one, we can see that v2 is equal to 12 centimeters per second and v1 is equal to 24 centimeters per second. Okay, there's a minor correction in data in the question. The angle of deflection for this one is not 53 degrees. It's supposed to be 30 degrees. So we'll just make a quick correction here. I'll tell you why, because it cannot be 53 degrees, because the 53-degree angle is giving us a result that the system's kinetic energy is increasing, which is logically not possible. So given that the mass of this one is 2.5 times the mass of M1, the mass of M2 is 2.5 times the mass of M1. So it's not likely that M2 will deflect by an angle as large as 53 degrees. So we'll take the angle to be smaller, 30 degrees, and let's check out the result now. So anyway, making this correction, let's just see the result that we get. So these angles are 30. So this will become so cos 30 is root 3 by 2. So 25 root 3 V2, this term will become. And sine 30, remember, is half. So it's become 20 V1 minus 25 V2. Okay, so this is what we'll get here. Now let's just check out the values that we get. With the adjustment made to the angle of deflection for the second body, which is much heavier, so not logically doesn't seem to be deflecting by such a large angle as 53. So instead we have taken it as 30. So now the deflection is through an angle of 30. So the final momentum being equated with the initial momentum, we get this relation. This is minus 25 root 3 V2 I cap. Plus 20 V1 minus 25 V2 J cap. So now we can see that equating the two, we'll get 360 equal to 25 root 3 V2 and 20 V1 minus 25 V2 equal to 0. That's equation 2. So this is giving us V2 as 360 upon 25 root 3, which we can write as this much, or you see is going to give us a much more feasible answer. And this is telling us that V1 is 5 by 4 V2. So tell us that V1 is 6 root 3 centimeters per second. You can see that there's going to be quite a loss of kinetic energy as a result of this. Okay. So that's the final velocity's magnitudes. So you can see that in our XY system, the final velocity for the first particle will become 6 root 3 J cap, deflected by 90 degrees. Okay. And the final velocity for the second particle will be equal to 48 root 3 into minus cos 30, because it's going in this direction, deflected by 30 degrees. So 4.8. Okay. Now, as far as the collision impulse is concerned, it's very interesting. As far as the coefficient of restitution is concerned, so for that we need to understand the center to center line when they come in contact, because that is the line along which we have to calculate the approach and separation velocity. This is the line of impact. Okay. So we need to calculate with respect to that line of impact, what is this angle, etc. So for that we can see that for the first body, the initial momentum was m1 u1 in this direction, and the final momentum was m1 v2 in this direction. Okay. Or rather m1 v1 in this direction. So the direction of collision impulse is this, and that is the direction along which line of action is acting. So this angle theta is tan inverse of v1 by u1. So it is tan inverse of 6 root 3 divided by 12. Okay. So it is tan inverse of root 3 by 2. That is the angle theta. Okay. So from that we can see that the approach velocity, so this particle has a relative velocity with respect to this of 2u1, and its component along this line where this angle is theta. So the approach velocity is this relative velocity is component along this direction, the center to center line direction or the line of impact. So it is 2u1 cos theta. Now from this we can see that cos theta is equal to 2 by root 7. Okay. So this becomes 24 into 2 by root 7, or 48 by root 7 centimeters per second. This is our approach velocity. Okay. Now likewise the separation velocity. So for separation velocity we have to understand that this has a velocity v1 in this direction, whereas this one had a velocity v2. This angle is 30 degrees, whereas just saw that the center to center line is this axis where this angle is theta. Okay. So that also means that this angle here is 90 minus theta. Okay. So our separation velocity will become v1 sine theta plus v2. Now v2's component in this direction will become cos 180 minus of 30 plus theta. Okay. So this becomes v1 sine theta plus v2 cos of 150 minus theta. So it becomes v1 sine theta plus v2 . Okay. So we had seen above that V1 and V2 were these values 6 root 3 and 4.8 root 3. So 6 root 3 into sine theta. Once again from this we can see that sine theta is root 3 by 7. Okay. Plus V2 is 4.8 root 3 into cos 150, which is minus root 3 by 2, into cos theta, which was 2 by root 7, plus sine 150, which is half, into root 3 by root 7. So you can see that this separation velocity is like this. So this is our separation velocity. So this comes out to be approximately about 4.1 centimeters per second. Whereas our approach velocity above we had seen was this much, which is approximately 18.1 centimeters per second. So now from that we can see that the coefficient of restitution, which is the ratio of separation to approach velocity, becomes approximately like this. So this is the coefficient of restitution. So this is somewhat complex kind of numerical problem of 2 dimensions. So it's taken us a bit of time to solve, but nonetheless, this is the general method of solving 2-dimensional collisions between 2 particles. Okay? And we'll discuss more about these type of questions. I will just leave you with some time to go through the solution of this whole section first. Okay, so that was the calculation of coefficient of restitution in this. Now, next up, let us look at another problem of an oblique collision. But this time with a little bit more detail about the geometrical type of calculations to do in it. So let's understand this. So let's say in this particular problem, we have two identical disks. And they're colliding on a smooth horizontal two-dimensional surface. So A and B are identical disks of mass m each and radius r each. Now B is at rest initially, and A collides with B with the impact parameter. I'll explain what this term impact parameter means. Equal to R. So if the coefficient of restitution is 0.5, we have to find the velocities of A and B just after impact. So the impact parameter here means this particular term, that if we see the line of action of the velocity vector being this one here, then that line of action of the velocity vector of A is at a perpendicular distance with respect to the center of B. This perpendicular distance here. This is called the impact parameter. And that D is equal to the radius of either disk. Okay, so from that we have to do this calculation. So I'll just leave you with a minute to go through the question and we'll discuss this in detail. Okay, so let's understand this question. So if we compare the situation of the two disks, the system of the two disks, just before the impact happens, so we compare the situation just before impact with the collision impulse during impact, and finally we'll compare that with the situation just after impact. So just before impact, we can see that the velocity of the sphere A is a vector like this, and the center to center line that is this axis over here. This is the collision, the line of impact for the collision, because when they come in contact at that point of time, you can see that the velocity vectors, or rather the collision impulse vectors, will be acting along this center to center line. Okay, so the impulse they apply on each other will be along this line. So that is why we say this is the line of impact. Whereas this is the line which is perpendicular to the line of impact. Line which is perpendicular to the line of impact. Okay. Now another thing that we see here is that geometrically, we draw this line of impact and compare it with the direction of, or the line of action of A's velocity. Then from the impact parameter which is given to us, that is this perpendicular distance, and the center to center distance which is 2r, we can calculate the geometry of this triangle. Okay, so let's magnify this a little. So you can see that in this diagram, the geometry of this triangle, we can understand. Let's just understand this in a little bit more detail. So now if this is the center to center line, or the so-called line of impact, And let's say this here is the line of action of A's velocity. This is the initial velocity of A's direction. So center of B to that initial direction, this impact parameter is D, whereas this distance here is 2r from the center of A to the center of B. So from the geometry of this, we can work out this angle theta. We can see that theta is sine inverse of D by 2r, which in this case becomes sine inverse of half. So that is nothing but 30 degrees. So this is the relationship between the initial velocity vector of A, which is along this direction, and the collision impulse acting on B, which is along this direction. You can see this angle is 30 degrees. Okay, so from that we understand that after impact, the final velocity of B will be along this line of impact, but the final velocity of A will be in some direction like this. Such that so this is VA and this is VB. So we now take the line of impact as our x-axis and the perpendicular line as our y-axis. Then conservation of momentum along the x-axis will give us the relation that mv0 cos theta is equal to mvb plus, now let's say this angle, some phi. So it is plus mva cos phi. So v0 cos 30, that's root 3 by 2, is equal to vb plus va cos phi. That is the first equation which we are getting from conservation of linear momentum along the x direction. Now, similarly, conservation of linear momentum along the y direction will give us mv0 sine theta in the first diagram is equal to mva sine phi in that diagram. So we know that v0 by 2, because theta is 30 degrees, we've already worked that out, is equal to va sine phi. So that becomes our second equation. And now we'll use the coefficient of restitution concept. For the coefficient of restitution, E is given to us as the problem E is 0.5. So separation velocity should be equal to 0.5 times approach velocity. So the separation velocity we can see in the second diagram is Vb minus Va cos phi. And that should be equal to 0.5 times the approach velocity in the first diagram, which is V0 cos theta. So this tells us that Vb minus Va cos phi is equal to root 3 V0 by 4. You can write this as, because theta was 30 degrees. So this becomes our third equation. And as it turns out, we have three variables to find out, Va, Vb, and phi. So we just compare equation 1 And equation 3. So by adding them, we can see that we will get VB as this much. Okay. And by subtracting them, we can see we'll get this much. Okay. And now from equation 2 and 3, or 2 and this combined, we have VA sine phi is equal to V naught by 2. So we can see that VA will become this much. Okay. And we'll also see that phi will become tan inverse of 2 by root 3. Okay, so this gives us the final velocities and the direction of in both in terms of magnitude and direction, because we found out the angle and all that for the two colliding particles, the two colliding bodies in this case. So another interesting result I'd like to emphasize from this kind of concept here is that if two identical mass particles, okay, make a perfectly elastic oblique collision, where the second one was at rest initially, then their final velocities are perpendicular. Okay. So this is a very important result, and let's discuss about this. So let's make a sort of a special case of the previous type of example we have taken, wherein that special case, if this particle A or the mass m is moving with a velocity v naught and hits another identical mass body or identical mass disk or sphere or whatever at rest, and the coefficient of restitution is 1, then what will happen is immediately after impact, so let us say our line of impact is this one here, and the initial velocity of this particular particle was along this direction. So if this angle is again theta, so what we can see is that after impact, If this has a final velocity v2, this has a velocity v1, where this angle is phi. So we can see that this time conservation of linear momentum along our x-axis will show us that mv0 cos theta is equal to mv2 plus mv1 sin phi in this case. Conservation along the y-axis will show us that mv0 sin theta is equal to mv1 cos phi. And the coefficient of restitution being 1 will show us that v2 minus v1 sin phi should be equal to v0 cos theta. Now, if we compare equation 1 and 3, we can see that what is basically happening is along the x-axis, it is a perfectly elastic head-on collision. So the first one's component, which is v1 sin phi, should become 0. And the second one's value, v2, should become v0 cos theta. They should exchange their momentum along the x-axis. Okay. So anyway, so the first equation is showing us that v2 plus v1 sin phi is equal to v0 cos theta. The second one is showing that v2 minus v1 sin phi is equal to v0 cos theta again, because the coefficient of restitution is 1. So from this we can see that v2 is simply equal to v0 cos theta and v1 sin phi becomes 0. That means along the x-axis, their momenta are just exchanged because there's a head-on collision. Okay. And of course, from equation 2, we have v1 cos phi is equal to v0 sin theta. So that's what shows us that after the impact, okay. Now again comparing this equation and this equation shows us that phi is 0. Okay. So if phi is 0, you'll realize that v1 is along our y-axis and v2 is along our x-axis. So v2 is actually equal to v0 cos theta along the x-axis and v1 is equal to v0 sin theta along the y-axis. So v1 is perpendicular to. So that is one way to interpret this perfectly elastic collision, which is oblique in nature, and understand the fact that the particles' final velocities are orthogonal or perpendicular to each other. Now, another way to interpret the same thing is that E equal to 1 also implies that kinetic energy is conserved during the collision. So, half m v0 squared so we have the relation that v0 square is equal to v1 square plus v2 square. And from momentum conservation, for the system, we have this implies that okay. Now, if you compare these equations, you can see that v1 plus v2 is equal to v0. So mod of v1 plus v2 be equal to mod v0. So this quantity should be equal to v1. Now compare it with this. So compare with this. So this implies that the dot product of the two vectors is 0, which means they are perpendicular to each other. Okay. So this is an important case of the oblique collision between two bodies. So with this, we will conclude the session today. And in the next version of, or the next episode of this series of lectures, we will look at some general applications of conservation of linear momentum and also variable mass system and impulse momentum theorem, etc. With that, we'll wind up this chapter. So wish you all the best, and that's it for today.